So today I am going to discuss about working principle and application of NMR spectroscopy. First, I want to say thanks to PCT 2020 team and Dr. Chinnakeshavalu. My special thanks to Dr. Chinnakeshavalu for giving this opportunity. So now I am going to my lecture. NMR has an application in a wide area of science and technology. For example, it is applicable in agriculture, medicine, hospitals, food technology, solid science, physics, structural biology, and structural chemistry. In this lecture, mainly I am going to focus on structural chemistry, how it is used in structural chemistry and how we can solve the structure of organic compounds and inorganic compounds, and we can find out the physical properties of molecules. Okay, so today I'm going to introduce about the NMR spectroscopy, sample preparation, working principle like spinning, tuning and matching, locking, shimming, and application of NMR spectroscopy. NMR, nuclear magnetic resonance. It's a phenomenon which is when the NMR active nuclei are present in the strong magnetic field, the nuclear energy level will be splitting. That is called Siemens nuclear splitting. So that time we are passing the radio frequency. The lower energy nuclei absorb the radio frequency and go to the higher energy state. After the radio frequency, the system relaxes back to its state of equilibrium, sending a weak signal that can be recorded. This is the NMR spectrum of principle. Then next I am moving on to the what are the nuclei NMR active. So if any nuclei having odd atomic number or odd mass number, all are NMR active, we can take NMR. If I am explain briefly means, if the number of neutrons and number of protons, if any nuclei has number of neutrons and number of protons, both are even, then the nucleus has no spin. These are the nuclei are not NMR active. We cannot take NMR. If the nucleus has odd number of protons or odd number of neutrons, these are the nuclei has off integer spin. These are the nuclei are NMR active. Example H1, B11, C13, F19, and P31. If the nucleus has odd number of protons and odd number of neutrons, the total spin of the nucleus is integer. These are the nuclei also NMR active. We can take NMR. So these are the samples we can take NMR. Now our sample is ready for our sample is NMR active. So first step is sample preparation. If you are making a good sample, then only we will get a good spectra. For sample preparation, if you want to do proton NMR, we need a 2 to 10 milligram of sample is enough. For higher concentration, will lead a broader signal. So this is the cinnamic acid proton NMR spectra. This is the higher concentration. The shimming is not good, so that's why the spectral lines are very broader. So I'll explain you later on what is shimming and all. For C13 experiment, higher concentration will give better spectra. For C13 experiments, we need a 10 to 50 milligram samples. For high molecular weight samples, we need a more concentrated samples. For C13 sample must be prepared with, for NMR purpose, we need to prepare the sample with deteriorated solvents for two reasons. One is for field frequency locking, and another reason is swamping the NMR signal. If you are using protic solvents, it will mask your compound signal. You cannot see any of your compound signal. So that's why we need to prepare the lower concentration. NMR is generally NMR is an insensitive technique. Okay, now our sample is ready. So next I am moving on to the NMR tube. First we were looking our sample is NMR active or not. Then our sample is NMR active. Then we know what is the amount of sample is required. Next NMR tube. This is the 1 minute. Actually, this is the NMR tube. Okay, so this outer diameter is the 5 mm. Generally, most of the people are using 5 mm NMR tube. Various types of NMR tubes are available. This length is 7 inch with 5 mm outer diameter. For boron samples, for boron NMR analysis, we can use the quartz NMR tube. These NMR tubes are made by borosilicate glasses. Generally, thin-walled NMR tube is preferable. It will give a greater testing precision and increase the signal to noise ratio. And thin-walled NMR tubes have minimal paramagnetic impurities that will support for shimming. Next one is the NMR tube cleaning. How to clean the NMR tube? NMR tube must be cleaned properly to get high quality NMR spectrum. Clean the NMR tube repeatedly, wash with water and organic solvents. Finally, rinse with acetone. We should not use any brush or abrasive materials for cleaning the NMR tube. If we are using this brush or abrasive materials, will make a scratches inside the wall of the NMR tube. It will affect the shimming. If shimming is not good, our NMR spectra is not good. So that's why shimming is the most important. I will explain you later on what is shimming and all. This is the NMR tube, and this is the 5 mm NMR tube. The length is 7 inches. The outer diameter is the 5 mm. Okay, this is the cap. Okay, so I'll explain how to prepare the sample and all later on. Sorry. Okay, so for cleaning purpose, we should not use any brush or abrasive materials to clean the NMR tube. It will make scratches on the inside the surface of the tube. This will affect the shimming. For drying purpose, we should not keep the tubes at elevated temperature. If we are keeping, it will reshape the NMR tube. So that's why we have to dry in the simple air drying is enough. If it's needed, we can keep it for few minutes. I mean, 15 to 20 minutes, we can keep it at high temperature, and we have to take it out immediately. Okay. Okay, so commonly used NMR solvents are 1 minute. Okay, the sample must be sufficient. Now our samples are ready. The sample tube is ready. Now next step is the solubility. Our sample must be sufficiently soluble in any deuterated solvents. We need a clear solution. Turbid solution will give poor NMR spectrum. If you are not sure which solvent to use, start with non-deuterated solvent until you find the appropriate solvent, because deuterated solvents are very expensive. The solution volume should be 0.5 to 0.6 ml, and the perfect depth is 4.5 to 5 centimeter. If it's not, we won't get proper shimming. Less volume of solution will give a bad spectrum because of bad shimming. Same high volume also will give the bad shimming. So that's why we need to make our solution 0.5 to 0.6 ml. Commonly used NMR solvents are CDCl3. It means deuterated chloroform, DMSO D6, D2O, CD3CN, acetone D6, benzene D6, toluene D8, THF D8, and dichloromethane D2. Most of the organic people are using CDCl3 as a solvent, but CDCl3 has only one deuterium atom. So deuterium search at start of the NMR experiment may fail for very concentrated samples. So that's why we need to prepare the dilute solution. Our solution should be clear. Dissolve the samples in deuterated solvent, mix it well, and transfer into the NMR tube. If undissolved particles are present in solution, we need to filter it in the solution and transfer into the NMR tube. For NMR purpose, in generally, we need to use single solvents. Sometimes our compound may not be soluble in single solvents. We need to use a mixture. If we are using a mixture of two different solvents for sample preparation, it is difficult to the NMR instrument for locking the solvent. If you, for example, if you are using DMSO D6 and CDCl3 as a solvent, you are locking with DMSO, but the machine picks the CDCl3 signal. Results, every signal will be shifted. So that's why instead of DMSO CDCl3 mixture, we can use DMSO CCl4 mixture, because CCl4 it doesn't have any hydrogen. Like that, we need to choose non-deuterated, non-protic solvents. For example, CCl4, CS2. If you are choosing a deuterated solvent with non-protic solvents like CCl4, CS2 mixture, we can use for NMR analysis. Generally, single deuterated solvent is recommended for good H1 NMR spectra. For other nuclei, we can do without locking, because proton spectral width is very small. So particularly proton spectra, if you are taking proton NMR spectra, we must use the deuterated solvents. Other nuclei, we can use non-deuterated solvent also, like chloroform, methanol, whatever solvent we can use. But particularly the proton NMR, we need to use the only deuterated solvents. For F19, P31 and those nuclei, no need for a deuterated solvent. If we have, we can use, otherwise it's not a problem. Okay, so now we made our sample. Then we are going to the instrumentation room. If we are going, before that, we need to wash our hands properly. Dirty hands makes dirty tubes. This dirty tubes makes our instrument dirty and we'll get a poor resolution spectra. After preparing the solution in NMR tube, wet the wipes with acetone and clean the NMR tube's outer wall. Okay. Once clean the outer wall, we need to fix it in the spinner. See, this is the spinner. This is called the spinner. Here, this is the already prepared good NMR solution. This is the depth gauge. Okay, this is our NMR solution. So we need to insert like this, and this is the depth gauge. We need to measure the height. This height should be center. You can see this mark. If it is not center, you won't get proper shimming. Okay, so like this, we need to measure. This is the depth gauge, and this is the spinner. This color marks used for measuring the spinning speed. We need to spin our sample inside the machine. What is the spinning? Those things and all I will explain you later. Okay, so this is the spinner, NMR tube, and depth gauge. Once we measured, then we'll keep it on the NMR instrument, top of the magnet. Okay, once we keep the top of the magnet with airflow, it will reach the probe head. Inside the magnet, probe head is there. This is the actually probe, external probe we have. Okay, I think you can see. If you are keeping the top of the magnet, it will reach here. This is the probe, it will spin. Inside the magnet, it will spin. This is inside the magnet. These are the things are happening. Okay. So various kinds of probes are available. So those things and all I will explain later. Okay, so now our sample is prepared. We kept on the NMR instrument. Our sample reached in the probe head. Once it reached in the probe head, the very first step is a spinning. Okay, the spinning can average out the homogeneous magnetic field. Why we are spinning? It will average out the inhomogeneous magnetic field. This spinning will lead for sharper spectral lines. Spinning will increase the signal to noise ratio. However, artifacts are called that spinning sidebands. If we are spinning too much, then we will get the spinning sidebands. So the optimized spinning rate is 20 Hz per second. So this is the example of spin on and spin off sample spectra. So this is the spin off spectra, and this is the spin on spectra. Once we spin on, the signal intensity increases 64 times. If we spin up, we won't get proper splitting. If we spin on, we'll get the splitting and signal intensity also increases. Okay. So, and one additional things, we are getting the spinning sidebands. These are the artifacts or noises. So we cannot avoid those things. If we are spinning too much, then the intensity also, it will be increases. As well as our sample, sample spectral line also increases, and same time, the spinning sidebands also increasing. So the optimized is 20 hertz per second. Next. Sorry. Next, once spinning is done, we need to tune. We need to do the frequency tuning and matching. It means if you are doing any nuclei, we need to tune the radio frequency. If we want to do the proton NMR experiment, we need to tune the frequency at 500 megahertz. When the tuning and matching optimizes the efficiency of radio frequency pulses and maximizes the sensitivity. This process is called tuning and ATMA or tuning and matching. People used to say in different terms. Okay, so how to measure the tuning frequency or resonating frequency or Larmour frequency? All are same meaning. Okay, if you want to do proton NMR in 500 megahertz machine, we need to tune the frequency at 500 megahertz. For C13, we need to tune the 125 megahertz. People are asking 500 megahertz how? Because every nuclei, the resonating frequency or Larmour frequency is differing. So if you want to do C13 in 500 megahertz instrument, the C13 frequency, we need to tune at 125.4 megahertz. Because it's every nuclei, the tuning frequency is varying. In generally, people are used to call the proton resonating frequency in the name of the machines differentiated in the proton resonating frequency. This is a table actually how to calculate the resonating frequency or Larmour frequency of particular nuclei. The Larmour frequency is related to the external magnetic field strength multiplied by the gyromagnetic ratio. Here omega is the Larmour frequency or resonating frequency, B naught is the magnetic field strength, gamma is the gyromagnetic ratio. Magnetic field is measured in Tesla. 1 Tesla equal to 10,000 Gauss. For example, 500 megahertz NMR, magnetic field strength equal to 500. We know the field frequency is 500, and gamma is the gyromagnetic ratio. Proton gyromagnetic ratio is 42.58. For 500 megahertz, magnetic field strength is 11.742 Tesla. Some other nuclei gyromagnetic ratio is given in the table. The high resolution NMR are not perfect prone drift. For next one is the once tuning is done, the next process is the locking. We need to lock the magnetic field because the magnetic field is a very higher value. Always drift will be there. Theoretically, it's per hour 10 ppm. It's drift. Drift will be there. For that, we need to lock the magnetic field. If we didn't lock the magnetic field, if you are doing the longer experiment, we will get the broader signal. If you are doing proton NMR spectra, in the line width is must be 3 hertz. If you didn't lock, then the peak width will be the 10 hertz. So that's why we need to lock the magnetic field. For that, we have a locking coils are there. It will support for locking. Without locking your sample, the drift cause the resultant sample peaks would apparently appear at different frequency for long running experiments. For that, we are using the deuterium because deuterium has a spin 1 nucleus. Its T1 is comparatively very low compared to proton. It's lower spin value, sorry, lower T1 value. So that's why we are using deuterium locking. Once locking is done, shimming. Already I told so many times shimming. Okay, shimming. What is shimming? Shimming is making homogeneous magnetic field in whole volume of our solution by magnetically or electrically. If magnetic field is not homogeneous, we'll get broader spectral lines, because if you are taking the solution 1 minute. Sorry. So this is the NMR tube we kept inside the magnet. In generally, due to the gravitational force, the bottom portion concentration is higher than the top portion. The outside magnetic field is already locked. This is a constant. Because of concentration differences, the downfield sample feel the different magnetic field. The top portion of the sample will feel the different magnetic field because of gravitational force. So we are spinning, still the concentration is not uniform. So that's why we are doing the shimming. That shimming, what will happen? The external external coils are there. The shimming coils are there. It will support for making the homogeneous magnetic field in top and bottom portion of the solution. If it's not, top portion, same molecule of top portion will give one line and bottom portion will give another line. Then we will get a broader, sometimes shoulder like signal also we will get. So that's why shimming is the most important. The shim coils are present in the probe head. This is the probe actually. So inside tuning and matching rods are there, locking coils are there, shimming also happening in inside. This is the most important part in the NMR spectrometer. Factors affect the shimming. Solubility of your sample. Your solution, your sample is not soluble properly, it will affect the shimming. Liquid height and position. We need to prepare the exact volume of solution. If it is less volume, it will affect the shimming. If solid particles are present in your solution, that will also affect the shimming. Viscosity. If highly viscous your solution, that will also affect the shimming. Radicals or paramagnetic materials are present in your solution, that will also affect the shimming. Solution of salts, that is also will affect the shimming. If you are making higher concentrated solution, that will also affect the shimming. And NMR tube dimension and cleanliness. If your tube is not clean, that will also affect the shimming. So that's why we have to be very careful with these things. Then only we'll get a proper shimming. Then only we'll get the good NMR spectra. Okay. Once we got the FID signal, free induction decay signal. If we are Fourier transform it, then we'll get the NMR signals. The NMR signals are collected in the form of time domain signals. These signals are Fourier transformed and get the frequency domain signals. The Fourier transform is the mathematical calculation. The NMR spectrum we will get in the chemical shift. The chemical shift is defined as nuclear shielding. Chemical shift is a function of the nucleus and its environment. It is measured to relative to a reference compound. For example, proton NMR reference is usually tetramethylsilane, TMS. TMS is the internal standard. For a chemical shift equal to observed frequency minus TMS frequency divided by instrument frequency. For example, in 500 megahertz instrument, 4 ppm equal to, if you want to calculate the hertz, 4 equal to observed frequency, the TMS frequency we are assuming as a 0 divided by instrument frequency 500. Then 4 ppm equal to 2000 hertz in 500 megahertz. Next, I'm moving on to the application of NMR spectroscopy. Through NMR, we can find out the structural property of the compound molecules using a 1D and 2D multidimensional NMR spectroscopy. And additionally, we can find out the physical properties. For that, we can do the variable temperature NMR spectroscopy and relaxation studies, T1 and T2 experiments, and diffusion studies. Through these diffusion studies, we can find out the chromatogram, NMR chromatogram, and we can find out the molecular weight distribution, and we can find out the molecular size, and all the information we can get it through the DOSY experiments. This is the simple proton NMR spectrum of ethylbenzene. This is the 1D NMR technique. In generally, the proton NMR spectra, x-axis is the chemical shift, y-axis is the intensity. In general, the 0 to 3 ppm aliphatic protons will come, 3 to 5 ppm olefinic things will come, 2 to 3 alkyne protons will come, and 6 to 8 aromatic protons will come. These are the splitting pattern will give the adjacent carbon informations. This is the ethylbenzene proton NMR spectra. This integral value will give the number of hydrogens present in our compound. We can integrate and we can find out the number of hydrogens. Next, this is the ethylbenzene C13 NMR spectra. In generally, the aliphatic carbons, it will give the information about number of carbons. It may be aliphatic or aromatic. It will give all the information. This, in general, the aliphatic carbons will come 10 to 70 ppm, 70 to 120 ppm olefinic carbons will come, 120 to 160 aromatic carbons will come. And carbonyl and quaternary carbons above 160, we can see. This is the dimethylacetamide proton NMR spectroscopy. Through this, actually, this is the dimethylacetamide proton NMR. Here we can see the 3 proton signals. 3 methyl groups are there. We can find out the 3 proton signals. In room temperature, the rotation speed is very slow. The CN bond rotation is very slow. So we can measure the NMR time scale. That's why we are getting in the 3 signals. If you are increasing the temperature, the rotation will, this rotation speed will be high. We cannot measure in the NMR time scale. We will get the 2 signals. With this value, we can find out the Gibbs energy. See, this is the high temperature, variable temperature, high temperature NMR spectrum of N N-dimethylacetamide. In room temperature, we can see the 2 methyl groups. If you are increasing the temperature, this will merge here. This is the coalescence temperature. 383 is a coalescence temperature, and keep on increasing the temperature, it will merge and we will get the sharper signal. With this coalescence temperature, we can find out the Gibbs activation energy using the Eyring equation. So this transition is happening in the molecule. In room temperature, the rotation is very slow. If you are increasing the temperature, the rotation speed is very high. This formula will give the Gibbs activation energy. This is the same low temperature NMR experiment. This is the one of the morpholine derivative. In room temperature, this is the room temperature NMR spectra. This all the axial and the equatorial will give the single signal, because in room temperature, the axial equatorial variation transformation is very fast. That's why it will give the single signal. If you are if you are decreasing the temperature, and we will get the separate axial hydrogens and the separate equatorial hydrogens. Once keep on decreasing the temperature, this 248, this is the coalescence temperature, and with this coalescence temperature, we can find out the activation energy, Gibbs activation energy. This calculated activation energy is 11.08 kilocalories per mole. Like that, we can find out the activation energy also with variable temperature NMR. In generally, the variable temperature NMR, we can do the plus 150 to minus 150. In any machines, we can do the variable temperature NMR spectroscopy. This will give the information about physical properties like Gibbs free energy, rate of the reaction. We can find out through this variable temperature spectroscopy. Next, DEPT experiments, distortionless enhancement polarization transfer. This is also simple 1D NMR spectra. DEPT experiments will give the information about proton attached carbons. DEPT experiment has higher sensitivity than normal 1D carbon spectra. DEPT is a double resonance pulse program. Polarization transfers polarization from excited nucleus to another. For example, here proton polarization transfer to the carbon NMR spectra. That's why its sensitivity is higher than the carbon. The proton pulse is set at 45 degree, 90 degree, and 135 degree in separate experiments. There are three DEPT experiments will be there. In these experiments, quaternary carbons are not present because the polarization power transfer from the proton. That's why it will give the information about proton attached carbons. For DEPT 45 experiments, we can see all proton attached carbons except quaternary carbons. DEPT 90 shows only CH carbons. We cannot see the CH2 and CH3 as well as the quaternary carbons. We can see only the CH carbons. For DEPT 135 experiments, we can see CH and CH3 in the positive direction and CH2 will be in the negative direction. We cannot see any quaternary carbons. These are the DEPT experiments. Here I'll show some examples. Okay, so this is the DEPT 45 spectrum of ethylbenzene. Here this quaternary carbon is disappeared. We can see CH, CH2 and CH3 carbons. This is the DEPT 135 spectrum of ethylbenzene. Here we can see these are the CH carbons, the aromatic ring CH carbons. These all are positive, and CH3, this CH3 carbon, this is also positive, and this CH2, this is the negative. Here quaternary carbon is not present, it's disappeared. And this is the DEPT 135 spectrum. This is the DEPT 90. Here we can see only CH carbons. We cannot see any CH2 and CH3 carbons. This is the DEPT 90 spectrum of ethylbenzene. Here we can see these all proton attached carbons, CH carbons. Here this CH3 carbon is disappeared, CH2 carbon is disappeared, and quaternary carbon also disappeared. This is the DEPT 90 experiment. This DEPT techniques will support for carbon information of our compound. These all are simple 1D NMR experiments. Next, I am moving on to the 2D, basic 2D NMR techniques. In generally, the 2D NMR techniques we will separate into the homonuclear and heteronuclear. Homonuclear we can split into again two divisions. One is the throw bond correlation and another one is the throw space correlation. This throw space NOESY and ROESY spectra, and throw bond COSY and TOCSY spectra. Heteronuclear HSQC and HMBC spectra. I'll explain one by one. First is COSY spectra. COSY is the first multi-dimensional NMR experiment. In 2D NMR spectra, the peaks are usually shown in contour format. In the COSY experiment, magnetization transferred by scalar coupling. The correlations appear when there is spin-spin coupling between protons, but where there is no coupling, no correlation will appear. If wherever the protons are attached with adjacent carbon, we will get the correlation. See, this is the simple COSY example. Cross peaks in COSY spectrum are between the protons that are coupled. See here, these two protons are coupled. It means these two protons are attached with adjacent carbon. We will get the cross peaks like this. It will give the information about which proton is coupled with which proton. See, this is the ethylbenzene COSY spectra. Sorry, this is the cinnamic acid. Cinnamic acid COSY spectra. Here, see, these are the protons are attached with adjacent carbon. See, these two protons are attached. These two protons are attached with adjacent carbon. So that's why we are getting the cross peaks here. This diagonal is normal simple 1D spectra. We are interested in this off diagonals, this off diagonal contours. Here, these two protons are attached with adjacent carbon. So that's why we are getting the cross peaks. Next, here, these protons are attached with adjacent carbon. So that's why we are getting the cross peaks here. Next, this is the COSY spectrum of ethylbenzene. Okay. Here also same thing. These are the CH3 and CH2 protons are attached with adjacent carbon. So that's why we are getting the cross peaks here. Same aromatic also we can get the cross peaks. So these are the protons are attached with adjacent carbon. This COSY spectrum will give the information about adjacent protons attached with adjacent carbons. Next one is the TOCSY, total correlation spectroscopy. This is also homonuclear coupling. This is also throw bond correlation. TOCSY gives correlation between distinct proton as long as there is a coupling between every intervening protons. TOCSY is usually used in a large molecule with many separated counter networks. such as peptides, proteins, oligosaccharides, and polysaccharides. Magnetization is transferred successively over up to 5 to 6 bonds. We will get the cross peaks. Correlation is interrupted by 0 proton or heteroatoms are present. We cannot see any correlations. This is the TOCSY spectrum of amino acid. This is the aromatic region, and NH amino acid is aromatic and NH region. So we can see the connectivity. See, these are the protons attached with the aromatic rings, and these are the completely connected. And this is the aliphatic region. In between, heteroatoms are present. That's why this is not connected with this one. Okay, so like this, we will get the TOCSY spectra, and we can find out the amino acids and peptides. Next, throw space correlation, homonuclear throw space correlation. First, I am going to explain about the NOESY, nuclear overhauser effect spectroscopy. The H1 nuclei may interact with another through dipolar relaxation process, will appear as a cross peaks in NOESY spectrum. This type of interaction includes nuclei that are directly coupled to one another, also nuclei that are not directly coupled but are located in a spatially closer. Wherever the protons are spatially closer within 5 Armstrong unit, we will get the cross peaks in NOESY. The NOESY spectrum is useful for larger size, larger molecules such as proteins and polynucleotides. The larger size molecules tend to tumble more slowly in solution, which means that the NOE effect interaction have more time to develop the NOE signals, and we will get the good NOE spectrum. Small molecule tumble more quickly, we won't get good NOE spectra. So that's why we have another technique called ROESY. I'll explain you later. This is the cinnamic acid NOESY spectra. See, these are the protons. These are the protons are spatially closer. That's why we can get the cross peaks here. This NOE spectra also like COSY spectra. This diagonal is a simple 1D proton NMR, and we are interested in this off diagonals. These are the COSY interfluorescence. These two things are NOESY signals. Wherever the cross peaks are present, those protons are spatially closer. It may be a throw bond, but it is within the 5 Armstrong unit. We'll get the cross peaks. Next, I'm moving on to the ROESY. ROESY spectrum gives the throw space correlation via spin-spin relaxation process. ROESY spectrum gives the cross peaks between protons that are spatially closer. The NOE effect is 0 for medium-sized molecule, so that ROE experiment is preferred for medium-sized molecule. The quantitative ROESY experiment used to measure the distance between the protons. This is the ROESY spectrum of amino acid. Here, this diagonal is same like proton 1D NMR spectra. This is the proton, and this off diagonal, this cross peaks are there. This will give the ROESY signal. This will give the proton-proton distance. With this, we can find out the spatially closer protons. Next, I am moving on to the heteronuclear correlation. First, I am going to explain the HSQC. The HSQC experiment reveals the chemical shift of 2 different nuclei directly bonded to each other. Example, proton-carbon, proton N15, proton P31, proton B11. The proton-carbon HSQC experiment is used to determine the proton-carbon direct correlations, where the proton spectra in F2 axis and the carbon spectra in F1 axis. HSQC is relatively sensitive than C13 experiment. This edited HSQC experiment provides the information of depth to 135 information. Same thing we'll get. This is the HSQC spectrum of ethylbenzene. It will give the information about proton attached carbons. See here, F2 channel proton spectra is there, F1 channel carbon spectra is there. These protons here, these are the contours present. Wherever the contours are present, those protons are attached with that particular carbon. See, this contour explains this proton attached with this carbon, and this proton attached with this carbon, and these are the protons attached with these carbons. Here we can see. So HSQC will give the direct proton coupling. Next, I am moving on to the HMBC, long range coupling. Heteronuclear, HMBC is the long range coupling. The HMBC means heteronuclear multiple bond correlation. Here we can see the 2 bond, 3 bond, and up to 4 bond we can see the correlations. HMBC experiment gives the correlation between carbons and proton that are separated by 2, 3, and 4 bonds. Direct 1 bond correlations are suppressed. We cannot see the direct coupling. C13 spectra displayed on F1 axis and H1 spectra displayed in F2 axis. The HMBC spectrum does not contain diagonal. Each proton signal can be correlated with 1 or more carbon signals. See, this is the HMBC spectrum of ethylbenzene. If you are taking this hydrogen, we can see the correlation with this, this carbon and this carbon. Again, if you are taking this hydrogen, we will get the correlation with this carbon, and we will not get any correlation with this carbon. So this is the HMBC, heteronuclear multiple bond correlation. Next one is the DOSY, diffusion-ordered spectroscopy. DOSY analysis used to separate the NMR signals of different species according to their diffusion coefficient. DOSY is used to analyze mixture of small molecules and oligomers. DOSY spectra are presented in 2D plot format in chemical shift in horizontal axis and log of diffusion coefficient on vertical axis. Each slice of DOSY spectrum corresponds to the one regular NMR, regular compound, simple compound. Diffusion coefficient and molecular size can be calculated by DOSY NMR analysis. Using the Stokes-Einstein equation, we can find out the molecular size. Here, R is the van der Waals radius of the molecule, K Boltzmann constant, T temperature in Kelvin, eta is the viscosity of the solution, D is the self-diffusion constant. This self-diffusion constant we can find out through NMR. The diffusion of molecules in solution depends on their size and shape. Smaller molecule diffuse faster than the larger molecule. This is the mixture of DMSO, methanol, and urea mixture, DOSY NMR spectra. See here, this is the diffusion coefficient value, and this is the proton NMR spectra. And each slices will give the, each compound will give the each slices. See, this is the urea signals here, and this is the DMSO signal, and this is the methanol signal. Here we can see the diffusion coefficient. From this diffusion coefficient value, we can find out the molecular size. It will be useful for polymers and oligomers also. Okay, I am going to conclude my presentation. Analysis of with this NMR techniques, analysis of molecular structure and identification of unknown chemical substances. Qualitative analysis, for example, polymer chemistry and quality control, food chemistry, we can use these NMR techniques. A mixture analysis, it will be useful in the food chemistry and biochemistry. And this dynamics, chemical reaction, rate of the reaction, we can find out through this dynamic NMR spectroscopy. Relaxation studies will be useful in the molecular mobility and interatomic distances. Those are the things we can find out. Diffusion coefficient values, we can find out the molecular weight of polymers and oligomers. Thank you.